In this section, we'll explore neural network fundamentals, focusing on their structure and basic operations. Neural networks are computational models inspired by the human brain. They consist of interconnected nodes or neurons arranged in layers. A typical neural network has an input layer that receives data, one or more hidden layers where processing occurs, and an output layer that produces the results. These layers are connected by pathways that transmit signals from one neuron to another. The more hidden layers a network has, the deeper it is. Let's examine what happens inside a single neuron. Each neuron receives inputs from neurons in the previous layer. These inputs are multiplied by weights, which determine the importance of each input. The neuron also has a bias term added to the weighted sum. The weighted sum passes through an activation function, which introduces nonlinearity and determines whether the neuron fires an output signal. Mathematically, a neuron computes the weighted sum of its inputs plus a bias, then applies an activation function to produce an output. Activation functions are critical components of neural networks. They introduce nonlinearity, allowing networks to learn complex patterns. The sigmoid function squishes values between 0 and 1, making it useful for probability outputs. However, it can cause vanishing gradient problems in deep networks. The rectified linear unit, or ReLU, outputs 0 for negative inputs and passes positive inputs unchanged. It's computationally efficient and helps resolve the vanishing gradient problem. The hyperbolic tangent, or tanh function, outputs values between -1 and 1. It's similar to sigmoid, but centered at 0, which can help with training. Now let's see how data flows through a neural network. Data enters through the input layer, where each neuron represents a feature of the input. For example, if we input values of 0.8, 0.2, and 0.5, these are received by our input layer neurons. These values then flow to the hidden layer through connections. Each connection has a weight that multiplies the input value. At each hidden neuron, the weighted inputs are summed with a bias term, then passed through an activation function, producing new values. This process repeats as data flows to the output layer, where the final results are produced. In this example, our network outputs 0.7 and 0.3. Through this series of mathematical operations, neural networks transform raw input data into meaningful outputs, learning to recognize patterns and make predictions. Now that we understand the fundamental structure and operations of neural networks, let's move on to the learning process. Now let's explore how neural networks learn. Data flows from the input layer through the hidden layers to the output layer. Each neuron calculates a weighted sum of its inputs and applies an activation function. The network uses a feedback loop to refine its understanding. When errors occur, the information flows backward through the network. This process adjusts the weights of connections, assigning higher weights to paths that lead to correct outputs and lower weights to incorrect ones. This iterative process mimics how the human brain learns from examples and corrective feedback. Recent advancements have expanded the capabilities of neural networks. Transfer learning allows a model trained on one task to be repurposed for another related task, saving time and computational resources. Few-shot learning enables models to learn from a very limited number of labeled examples, which is more similar to how humans learn. These advancements, coupled with increased data availability and computational power, are driving the continued growth and adaptability of neural networks. These innovations are making AI smarter and more useful across various applications.